Super, thank you. This is a talk on gradual verification and how we're building this new kind of verification system to assure software incrementally. This was work led by my graduate student, now graduated, Jenna DiVincenzo. She's a assistant professor at Purdue now, but also a large team of other people, including Hemant, as he mentioned. Today, since this is IWACO, I'll be talking about the particular role that ownership plays in this system. Let me start by motivating this by the problem of verification. Let's say we want to specify some kind of system here. This is Daisy, the programmer, and she wants to verify that find max actually returns the maximum of a list. And so she writes an insurance clause that says the result is the maximum of the list, and meaning it's greater than or equal to every element, and also that the list contains that, right? So we don't just pick some arbitrarily high number. And so this ensures clause turns into essentially assertion at the end of the function. And we could check this with dynamic verification, which checks it for every run. But of course, we might want to make sure that this holds for all possible runs. And of course, the cost of dynamic checking might be significant, right? In these two functions, you might imagine might traverse the list, and so we would incur kind of an O of n overhead on checking, not even beyond what it takes to implement the function. So we could apply static verification instead. But of course, unfortunately, it's a little bit naive to expect that most static verifiers would just be able to verify an assertion like this, because we do this and we get a bunch of warnings, and it's sort of reasonable that we would get those warnings because actually we have to put it in a precondition, right? This code won't work unless the input list is not null. And in fact, for most verifiers to prove software that's sort of interesting, maybe a little more interesting than this, they probably require some help, right, in the form of loop invariants and maybe some lemma functions, some folds and unfolds, which I'll talk about. And so there's a lot more work for Daisy to do in order to prove this correct with static verification. What we're going to do instead is try a technique called gradual verification. And gradual verification is going to allow us to leave out specifications, and we'll check them statically. We'll check the specifications we do put in statically wherever possible and dynamically otherwise. So now, actually, our original specification is sufficient. If we leave out the requires, that just means requires question mark. And what question mark means is this is a specification we have not given yet. It's unknown. And so the gradual verifier, it still can't check much statically, right? But it will at least provide dynamic feedback, right, by doing dynamic checking in this form. Now we could then extend the specification with more and more clauses, right, to more and more information. So we could say, yes, actually, I know that the input list is not null. That might be important. And as we do this, then and we could add some loop invariants. Eventually, we could add the folds and unfolds and lemmas. As we add each piece, we get more and more static verification until when we have the entire thing specified, we have a fully static proof. But Daisy can stop at any point, right, when she believes she's achieved high enough assurance. Just as an example, this is, of course, a trivial example, but most of the verification conditions from this code can be statically verified with only half of the lines of specification code that we would need to verify all of them. Basically, there's a lemma at the end that is a lot of specification, right, that fills things in. So you can get quite far towards assurance, at least in this notion of percentage of verification conditions checked statically, with perhaps a minority of the annotations that you would need to check everything, which is potentially quite nice. And in fact, you can get into memory safety already after just 13 lines of specification, about 40% of the work. Everything except the lemmas is 86% right, and then the full spec is 100%. So to summarize, the problem that's motivating this work is that dynamic verification is low cost to the programmer, but we don't get any feedback at compile time, and we don't get any static guarantees, and of course it can slow down the program, sometimes a lot. On the other hand, static verification pays off only after a ton of work, right? Static verification can be 10 times as costly as writing the program. We have data on this from SEL4 and CompCert. And it requires basically an inductively complete specification, right? If the spec is incomplete, you'll get a warning, right, saying that you have to specify more things. It's kind of viral, right? And the same, if you think C++ const is viral, try Daphne, right? You might even think of these as false positives, right? It's not that your spec is incorrect; you just haven't proved it yet, right? And so with static verification, you don't also, by the way, you don't get any feedback on incorrect specifications unless there's a static inconsistency. So what we'd like to do is get more incremental payoff for incremental specification work and the ability to focus on the most important properties of the most important components first. And gradual verification is going to give us the ability to do that, much as gradual typing allows us to say, oh, in a dynamically typed language, let me add some types to the components that I care the most about, right? And our work is directly motivated by research in gradual typing. And so we want to provide early feedback on mistakes, both compile time based on the specs you've put in, and runtime, because we can run incomplete specifications. We'll check any specifications that aren't checked statically and give you feedback on them immediately, right? So in some ways that might be earlier than static checking, right? Which might not tell you about those things. Finally, we have some nice properties. I'll talk about these in the next slide. There's a property of soundness, which says all specification violations are caught either statically or at runtime. There's conservative extension. So if a specification has no question marks and it verifies, then the code is correct, right? And that's a static notion of soundness. The gradual guarantee, right, which is a standard property of many well-designed gradual type systems. If your specs are a subset of a correct spec, that is, if you're sort of on the way but you haven't gotten there, you won't get any errors either statically or at runtime. And then finally, pay as you go, right? This one's a little harder to verify analytically, at least in our case, but the idea is that hopefully the runtime checking cost, well, it'll first probably increase as you add specifications because you have to check those specifications, but eventually it decreases as those specs become statically verifiable. And we have some evidence for this, which is in a Toplas paper from earlier this year. I need to update the slide with that citation, actually. I won't talk about that today because I just have a short slot here. Let's talk a little bit about, though, how gradual verification works. And I'll start actually with ownership. So why is ownership important to verification? This is maybe preaching to the crowd for some of the IWACO old-timers, but maybe there's some people who haven't seen ownership all that much before. So let's look at a very simple property of a simple system. Here we have a counter. It has a field x, and we're passing it to an increment count. And I might write, actually, in our gradual verification system, we can write a spec that says, hey, coming in x count is n, and coming out x count should be n plus 1, right? And maybe some other things that I've left out with a question mark. Now, if we know that x count is 0 and we increment the count and pass x, then we know that x count is 1. But let's say y count was in scope. It used to be 0. Is it still 0, right? Well, I don't know. It seems like it should be 0 because I incremented x and I didn't increment y. But of course, if x and y point to the same counter, right, the same object in Java or in C, then y's count will have been incremented. It will now be 1, right? So we don't know. And this is actually a problem that stymied verification for maybe 3 decades. And the solution was separation logic, and we're using a variant of separation logic here, which builds ownership into the logic. So this is about ownership. So the rule is that you can't change the fields of an object. In fact, you can't even reference or talk about the fields of an object unless you own those fields. So how do we express ownership? There's this access predicate, access of x arrow count. So this idea comes from the idea of implicit dynamic frames. And access of x dot count says I own the field x arrow count. And so to even talk about x arrow count equals n, we have to have access to x arrow count. Okay? And then, of course, we want to return ownership to the caller, so we'll also put access of x arrow count in our insures clause. And so now, if we know that we have x and y, then we can say, well, I access x arrow count, and x arrow count is 0, and I access y arrow count, and y count is 0. How does this help me? Well, the other part that comes from separation logic is this special kind of conjunction, right? Separating conjunction star that says if there's an access on two different sides of a star, then those must be two disjoint fields in the heap, right? And so we know x and y cannot alias because their count fields are different, like different pieces of memory. And so what that means is when we call increment count on x, we'll just pass the access to the x. We'll keep the access to the y. We know they're distinct, and so we know that y's count is 0 at the end. Okay? So that's why ownership is critical to verification. It allows us to talk about, what parts of the heap might be changed by a given function, increment count in this case. Okay? And if you're wondering, this spec is actually okay because question mark can include access to x arrow count, right? It's incomplete, and the complete version includes access of x dot count. Let me talk about an example that gets a little bit more interesting and also includes ownership. So here I have a predicate that says a list is acyclic. And the idea is that I have an acyclic list, and then I might add a node to the front of it, and then I'd like to assert that the list is acyclic again. So what does acyclic look like? Well, we define a predicate that operates on the root of an acyclic list, and the predicate tests whether the root is null. If the root is null, then we're fine, right? An empty list is acyclic. Otherwise, we assert ownership of the value and next fields of the first element of the list, the root of the list, and we assert that the rest of the list, acyclic, is root arrow next, right? And so we have these accessibility predicates again, permission to access those heap locations, again, ownership, just in logical form. We have a separating conjunction that says these fields are all different, and importantly, the access to this first node in the linked list is separate from the acyclic of the rest of the list, right? And so that's how we know the list is acyclic, right? The first node is different from all the rest, and that's the rest is acyclic too, and so iteratively you get that the whole thing is acyclic. Okay, so that's that specification. Now we can see how we use it, right? So let's say Daisy is writing this list insertion program. She starts out with an acyclic list. When she allocates a node, then we learn since this allocation succeeded. If it didn't, we'd have gotten an exception and we wouldn't be here. So we know that L is not null, and we own L's value in next fields. L.next is the old L, right? And so that's still acyclic, right? Because we didn't change that at all. So now if we look at this predicate, we see that the thing we know about L is exactly what we need to know to show that L is acyclic. And so we can do what's called a fold operation, which takes basically the pieces of an acyclic definition, the right-hand side, and folds it into an acyclic predicate. And now we can say, okay, I have an acyclic list, happens to be one element longer. I didn't specify that. I could by putting like an index on the acyclic predicate if I wanted to. So that's how we prove this code statically. But we could also make it gradual, right? So if Daisy didn't specify that the input list was acyclic, she could have just written a question mark. And then we allocate a new node. We know that it's that we own the heap portions for that new node, and that it's not null. And we also, retain some unknown information that we had before this allocation. Let's say we want to fold the acyclic code again. Well, we have part of this information, right? We have that we own access lval and lnext, and that L is not equal to null. So we're in that second case of the acyclic predicate, but we don't have acyclic of lnext, right? And so, but the nice thing is that we can get that from the question mark, right? So the static prover is going to optimistically assume that we know acyclic of L.next, so we can do this fold successfully and finish our code, right? And then what's going to happen is later on we're going to fix things up by checking dynamically that this missing piece is actually true at runtime, right? So we will eventually check this soundly, but it'll be a combination of the static and dynamic checks. Okay, so one thing that's interesting about this, because we're trying to do dynamic checking, is we have to ensure all specifications are executable. And one of the most interesting bits of that is actually the ownership, right? So one of the things we do is we check that we can assert access of x.f. How do we check that? Well, we need a list of what the currently executing method owns, right? And so that's basically, there's a set of object field pairs. When we assert access of x.f, we verify, do we actually own this field? Anytime we assert a separating conjunction and we want to check that at runtime, well, we have to basically see, do we own all the things over here? Do we own all the things over here? And do they overlap, right? If they overlap, that's also will be an error. There's some other details, disjunction. We have a special form of disjunction. Well, we use if instead of disjunction because it makes things more kind of, they're easier to check. We could check disjunction too, but it turns out we get exponential checking in the presence of ownership. So that becomes pretty important to know which branch of a conditional you're in. And this is usually not like a big burden. A lot of static provers also use if instead of disjunction in their proof language. Another thing that's interesting and also interacts with ownership is recursive predicates. So like this acyc predicate, if we assert that, how do we check it? Well, basically, the acyclic predicate is a recursive predicate, and so we can turn it into a recursive function that just kind of goes inside until we get to the end of the list and checks that we own things all the way, right? Now, what's interesting is it would be kind of bad if we asserted something at runtime and it didn't terminate, right? Because our program would then stop while we were doing a runtime check. There's a nice, elegant solution there, which actually came to us from ownership. In our system, when you define a abstract predicate, in any recursive case of that predicate, you have to assert the ownership of at least one heap cell. And if you think about it, that means every time you unfold the predicate dynamically, you're eating up one more cell of the heap, and eventually you get all of them, right? The heap is finite. So you might wait a long time, right? If you're traversing if your linked list is using all the memory on your machine, it'll take a long time. But every time you go through that linked list, you'll assert the ownership of a new cell, and eventually you'll get to the last one. So that's kind of a fun trick. I guess I have some slides on producing dynamic checks, but I kind of talked about that, right? This is the part we know statically. We're trying to get acyclic, and so we do what's called, we do a dynamic check on the acyclic of L.next. There's an interesting theory issue here, which is that our dynamic checks are what's called equi-recursive. We basically treat the predicate as equivalent to its unfolding, whereas what we get in what we have in the static world is iso-recursive, where you have to explicitly kind of fold and unfold to look at the inside of the predicate and then look at the outside of the predicate. And so some of the interesting theory in this system was actually getting those to match up, making sure they did match up in our system. Let me talk a little bit about the last technical topic here, a little bit about how we dynamically verify ownership. So like I said, we have an ownership set, and let's say we have a couple of lists, X and Y, in main. And we'll keep track of, that main owns all the cells of X, those are the green cells, and all the cells in Y. And let's say these are acyclic and separated. Now, we call a length function. Requires acyclic of X, right? And so our stack above main, we have length. And what does length own? Well, we passed acyclic of X into it. And so our runtime system is going to actually, kind of enumerate all those things that are in X and pass their ownership to length, right? Because main still owns Y, we want to make sure that length, can't change it. In this case, length is probably just computing the length, so that's fine. But it could be ill-behaved, so our runtime system will make sure it works. On the other hand, if length has a question mark as predicate, then that means maybe it accesses X, maybe it accesses Y. We don't know what the spec is, so we don't want things to fail because we haven't specified the spec, and so we optimistically pass the ownership of everything to length in that case. Okay, so it's kind of an interesting approach to get this gradual guarantee, right? That code will not break unless we have kind of a proof that there's a problem with it. This actually leads to a very interesting application, which I haven't seen in other work on ownership. Let's say you want to restrict the ownership of some code, right? So here, back to my counter example. Let's say I have restrict ownership. From main, I create two counters and I call restrict ownership. And restrict ownership just takes ownership of X, right? And let's say X is different from Y. Now I call do compute. Do compute is completely unspecified, right? I have question mark and requires and ensures. Maybe it calls some other things, those are unspecified. No static checks, okay? But the runtime system is going to make sure that do compute only touches X, because that was the only thing that the caller had permission to, and the caller can only pass things it has permission to its callees. So you can make sure the whole call tree only accesses some piece of memory that you want to, which I think is kind of cool. Okay, so we're just, I think I'm at the end of my slot, so I'll just say we have an implementation of this. It's built on top of the Viper infrastructure. We extended it with some gradual verification techniques. So we extended their intermediate language with gradual specifications that have question marks. We extended the symbolic execution with an optimistic approach. And we had the optimistic checker generate dynamic checks for soundness at runtime. And then we connected that to a front end in a subset of C, which does the checking. So thanks to Jenna and my other awesome collaborators. And I'm happy to take any questions about the work.
Hi. Yeah, great talk. You mentioned all specifications need to be executable. I imagine there are some cases where you want a specification, it's not executable, but you'd be fine if it was only ever verified statically. Is that possible in the system?
Yeah, that's a great question. We have not thought about that. Yeah, I think, if that specification only showed up in statically verified code and it was never called from dynamically verified code, then and probably never called out to dynamically verified. Well, if it calls out to dynamically verified code, that's probably also fine, as long as like the interface to that dynamically verified code doesn't depend on that specification construct. So just thinking about it on the spot, I think you could do that, but we haven't worked it out. So yeah, it's a really interesting question.
Thanks.
Future work.
Hi. So I can imagine that I might write a specification for a function, and I don't know. I don't know something about. I might have a precondition that's not strong enough, and so I put a question mark in there, and I call it from some other function, and so I guess what you were saying was, in this case, this call kind of like eats all of the the dynamic version of the like accessibility predicates that I have around.
Yes.
But in this case, like, I mean, is there any way that I can distinguish, like, oh, I don't know about what ownership that I want versus there is some kind of bit of the functional part of the specification that's missing? Because I can imagine that,
Yes.
I don't know, otherwise, it eats all my tokens, and then I get an error, because that's because I lost all my accessibility predicates, and not maybe because I couldn't satisfy some precondition. I don't know if that makes sense.
Yeah, that's a good question. So one piece of that we've thought about, right? And actually one of the reasons we built on implicit dynamic frames rather than separation logic is that it separates the ownership from the assertions about the code. And so you can make assertions about the code and not say anything about ownership, leave a question mark for that. You can also talk about your ownership and leave a question mark for the assertions. So that part, it was an intentional design choice, and is a very nice feature of the logic that we're building on, that we kind of inherit and built the system to work around. I hear another piece of your question, which is, what if I want to assert ownership of some heap but not make specifications, but I don't want to use a question mark for the specifications because that could include ownership. Yeah. We have not thought about that. Just spitballing it, I think it might be possible to do that with kind of a design pattern or a mode of use of our system, but yeah, I'd have to check. I'd have to look at it in more depth.
Thank you.
Thanks.
Okay. So I was just going to ask, the difference between implicit dynamic frame and separation logic, which I think you already answered to some extent.
Yeah.
The other thing is you mentioned higher order function. I just like to point you to work that we did recently in FM24 on how to extend the logic to higher order functions. Yeah.
Excellent. Okay. Yes, we would love to look at higher order functions. We have not done that yet, and building on an existing logic would be great. Maybe we can talk afterwards.